So, let us look at this model at a very high level and then go into the details of that in the next slide. So, as we do in any model, let us define the fundamentals. So, input is a sequence of words, okay, and then the size is given here, that is length of the sentence. And then we have a target sentence which is again a sequence whose length is m. So, we can have a longer sentence producing a shorter translation or a shorter sentence producing a longer translation as well. So, this we need to be keeping in mind, right. So, the sentences are not of the same size. Okay, let us define the hidden units. Okay, so, these are all the vectors that we are going to have in the neural net, and then this one could be a LSTM or a GRU. So, the hidden units could be a cell which is a LSTM cell or a GRU cell that we saw earlier, and then now there is a new one that is coming in, it is a bidirectional one, right. So, in the bidirectional model what happens is there are layers of hidden units, and then one set of hidden units will learn from the last word to the first word, the other one will learn from the first word to the last word, right, and each one of them are connected this way too. Okay, so, this is another model where you can connect these two layers in the upward direction as well. So, one set of units learn from the last word to the first word, other one learns from the first word to the last. So, we know that this hidden units are the representatives of our input. So, connected through the embedding weights, right, and then these words are fed using our embedding, meaning that we are not going to be using a one hot vector and then inputting it. So, we are going to be looking at the words from the embedding table that we have created earlier, right. I am sure you remember that. So, embedding is nothing but the vector that represents the word, not only that word, it also represents the contextual information related to the words in the entire vocabulary. Okay. So, that is what we are going to be feeding. Some embedding sizes would be about 600, some use 1000, or you can also use as low as 100 as the length of the embedding vectors. So, that is what we input, and H1 to HT they represent the input embeddings, and then we have to create the alignment which we want to use for the translation, right. So, how do we create the alignments? Let us look at the decoder. The decoder is this, and then these are all the hidden states that you compute. This hidden states are computed based on the context that we are going to be getting from the hidden units, right. So, we worry about this in the next slide. So, we assume that we have computed the attention scores, okay, and then we created a weighted sum of the attention score which we call as the context. Context is the weighted sum of the H, okay, of this input, and also we are going to be getting some more values coming in from the decoder. Okay. So, that is where we spoke about peeking into the input side, right. So, let us use that as, I am just using some notation here. So, the context is not just about the weighted sum of the hidden units that are coming in from the input side, but also it contains some values from the decoder, right, and then that's fed into the state again for you to create the next output. Okay. So, now let us look at the SI. SI is the state of the hidden unit in the decoder, which is a function of the previous state, function of the previous input and the context that we are creating it. That is what is going in here as the. So, let me use a different color. So, this is what is going in as a input to the hidden state in the decoder. Okay. All right. The CI is our context vector they are going to be creating based on the hidden states, based on the input coming in from the decoder, and that is again fed back into the hidden state of the decoder, and then finally our output is created. So, let us look at this first from the equation perspective and then see a better diagrams. Okay. So, what are we going to be doing? So, we are going to be conditionally getting the output, right. So, this is a conditional probability. The yi is obtained by using the previous output values given the input sequence. Okay. So, it can be written as a function. So, let me just write one here. So, this is our decoder. So, we are going to be getting the output. Let us say I am translating from French to English. This is our start of this sentence. I am just marking it as a $. This is a function of the previous value. This is the start of the symbol is our previous value here, and then it is going to be the value that you are computing based on the context and the SI. Okay. So, let us assume that this is your SI. So, we have the CI coming in into this, and then finally, we have a softmax which will give you this output. Okay. So, this is the standard network architecture you would have seen, correct, and this is what we are going to be using. Okay. So, the output word in the decoder depends on the previous word, the hidden state and the context coming in from the encoder. Then SI is the function of the previous state. This should be yi minus 1, the previous output and the context coming in from the encoder, right. And now, we need to find out what is CI. So, actually we are coming from the top here. So, we found the conditional probability of yi, and then for us to find that, what do we need? We require yi, Si and Ci. To get Si, which is a function of the previous state, right. So, let me use this standard model, and then it gets Ci from the encoder, okay, and then you compute the Si. All right. So, this is from the decoder side. So, how we could compute Ci? Ci vector is our context that we are inputting into the decoder, correct. So, we now have to come to the encoder side and then see how Ci could be computed. You remember we saw there are AIs going in, right, and then this is the weighted sum I told you earlier. It is the weighted sum of the input unit, input hidden unit and another value that we would be computing now. Okay, so what is alpha I? Alpha I is our annotation for Hj, which is computed using a softmax. So this is a softmax, right? So what is Eij? Eij is now coming from the decoder. Got it? So this is our decoded hidden value from the previous state, and then we are computing Eij using the previous state of the hidden, or rather previous state of the decoder and the current state of the input or the encoder here, right. So this is our alignment model. So this is the alignment model which we are computing. So now coming from the bottom to the top, so let's look at this from here. Okay, so here let me remove some of these. So we are going to be computing Eij here. So using this, Eij is a function of Si and Hj, right. So Ei is going to be computed using this state and the hidden values that are coming in here. So whichever state you are, this is now Ei1 is computed using H1, Ei2 would be computed using this, and so on. And then I represents the hidden unit of the decoder. Okay. Is this clear? So I think a little confusing because we are coming from the top. So now let's go to the diagram where the explanation would be a little more clearer. So now I have actually expanded what we saw in the previous diagram. So now we have the encoder and this is our decoder. Okay. I have just assumed about 4 units. Okay. And then the translation is going to be for the set of input, the translation going to be the book is on the table. Okay. So we are going to be computing the first one, which is the, right. How do you compute the? That is where we started from the original equation, and then we computed Cij, and then we found what was Aij, and then what is Eij, and so on. So now we go from the bottom to the top. Okay. So this is our Si minus 1. Let us assume that this is our Si minus 1. Okay. So taking the value from here and then value from here, right. So we do a dot product of this. Eij is nothing but the dot product of Si minus 1 and H1, Si minus 1 H2, Si minus 1 H3, Si minus 1 H4. So we compute a value, right. So it contains each one will contain some, let me just write it in terms of some numbers, I am making them up. Okay. So Eij is written as a vector in this form, which could be okay. So each and every one is an element. Okay. So this could be Ei1, Ei2, Ei3, Ei4. Okay. And then we take a softmax of this vector. Okay. So once you take the softmax of this vector, the sum of all those values would be equal to 1 here. Okay. And you know how Aij is obtained. Now we know how Aij is obtained here using this formula. So we got this, correct. Okay. So we found how to get this Eij. We now know how to compute Aij, which is a softmax of all the values coming in from the Eij values, and then we compute the weighted sum of all these Aij values and provide a context vector. So, this now Cij is nothing but the weighted sum of these values and the input state. Okay, so, now we take this and then use this. So, this is one way of doing it. The other way also is to take the value from here and then do it. So, there are multiple ways of actually creating the context. One, directly taking the value from this and then creating a weighted sum, or you can also do it this way. Okay, so, what we have seen so far, right, when we compute the values of Eij, Aij and Ci, now we know that the decoder is trying to find out how can I really identify who is aligned with me at this particular time slot. Okay, this or that. Okay, so it could be this, or this could be this word. I am sorry, I should be using either this word, second word, or third word, or fourth. So, it is trying to peek into the input or into the encoder to figure out how to really align with that. During the training process, automatically they get adjusted, the values are adjusted, and we will finally get the alignment matrix in the right form. Okay. So, once you find a Cij, which is nothing but the summation of all the Aij's and the Hij. So, this is again a vector. You feed that into the decoder. Okay. So, use it to compute y t, okay. And then there is a softmax that you compute, and finally you get the output as the, right. So, here this diagram is little more elaborate when compared to what we saw earlier, and this explains clearly how each values are computed. So, I have given you all those computations in the slide itself. Okay. All right. So, when we compute it in this form, so how do you go to the next stage? Okay. So, we have done it for the first word, right, starting with the first word, and then for the second word again we do the same thing, taking this Si and then computing Eij and then computing Aij, creating a new context vector. So, this context vector which you are creating is with respect to this, correct, and then use this to it should be this, it should be this, it should be this. It is fed into the second stage, and then later you use a softmax by computing all these values here, and then say that this is book, and then here we are going to be having a j1 theta, j2 theta, we are computing the error every time, right. This is the training process, and then third what will happen is you take this one and then start right. So, that means now the third word is important, and it is now trying to peek into the alignment space to find out which set of words in the input is aligned with this. Okay. Then now the context is created, there will be new one, and the input for this also is coming in from the previous word. So, we keep going and going in this fashion until we find the end of the sentence. Okay. So, every time we keep computing it. Okay. So, there are multiple ways of doing this, we will talk about this process of stochastic gradient descent or batch processing or mini batch at the end of this session. Okay. So, the idea is to calculate this and then minimize the error, so that the weights are learned at the end of the training. Okay. So, this is what Bahdanov has created. So, now let us look at this slide again to understand what we have done. So, here the alignments are explicitly computed that we saw, right. So, we are trying to peek in from the decoder into the encoder and then trying to compute the alignment vectors. The alignment model also is trained along with the translation model. So, there is no separate model that we are creating like what we had done in the SMT space. So, alpha ij is the probability that the target word yj is aligned with the source xj. I am sorry, aligned with the target word y and the source. So, that means we are trying to find yi is aligned with xj. You remember the alignment we used to have x, y, z, a, b, c, right. So, alpha ij is the probability that the target word yi is aligned with the source xj. Ci is the expected annotation over all possible annotations that we have. That means, when you compute the Ci, right, so it is computed as the weighted sum. So, it is the expected annotation over all possible annotation that you have for that particular time slot. Eij reflects the importance of the annotation Hj with respect to the previous hidden state. Okay. So, this enables us to calculate the next state, which will in turn generate or predict the next word. So, during the training, the decoder decides which part of the input is important to generate respective translation, rather than depending on the encoded vector of the entire sentence, right. So, in the model that we saw earlier in the previous session, we need to have the entire context available for you to do the decoding. In this case, now it is not required. It can figure out which part of the sentence or the encoder, which part of the encoder is useful, and then starts aligning it automatically. Decoder has control over the input sequence and selectively learns to align words and phrases automatically. So, again, for you to get to this level, we need to have a very huge corpus, right. Then only the patterns would become very clear to the machine. During the machine learning cycle, the patterns will start emerging clearly for this system, and it starts to align automatically. All right. So, what we actually saw was just the attention model, where we had looked at the global attention, right. So, that means we looked at every state of the encoder. So, we have not left out anything. That means, we have taken into consideration every state in order to compute the attention score, right, and that is what we had used to compute or predict the next word, right. So, there are variations to this. Instead of keeping the attention for all the input hidden states, so can we partition it? So, that is the next stage, right. So, the attention is coming in through this. This is one way where we capture the attention score for the entire input hidden states initially, using the state coming in from the decoder, right. So, instead, can we just look at some of these, not all of the hidden states of the encoder. So, So, what we saw earlier was a global model. So, then now we need to see if we can localize that. So, still more control in terms of figuring out which part of this I need to have. I do not want to really look at every piece of Hj that I have in the encoder. I only want to look at only one portion of that. So, there comes the local model, where we are going to be doing the translation with local attention. We will just see in the next one. So, this computation is very similar. Actually, you would see variations in the equation, but they are almost the same. Some would write it in this fashion, the attention score, okay, and then Ht is nothing but what we saw as S in the previous case, and so on. So, do not get confused, but if you look at the right side of the equation, you will know very clearly what they really represent. Okay. So, now this is what I was talking about in the previous slide, the translation with the local attention. So, rather than peeking at every possible hidden state, I want to only look at portions of that. Why are we doing this? You remember in the RN model, if this sentence is too long, it is not able to really remember the first part of the sentence, right, because of the decay in terms of your gradients, right. So, even if you use LSTM or GRU, you can, if I write it, right. So, you can see that at this time slot you will have a good representation of that particular state of the input, and then slowly and slowly steadily it decays. So, when your word is here, this particular state will not really know very much about what is there in the H1. Let us say if this is Xt. This is the problem with the RNN, right. So, we need to overcome this. So, we have several mechanisms to overcome. One is the vanishing problems are overcome by GRU and LSTM, but still we have the decay in terms of or the degradation with respect to knowing something beyond certain states is another problem for this. So, can we somehow overcome this? So, that is where the local weights are coming into play. So, in this case what we are doing is, instead of looking at every piece of information that is coming in, only look at what I need. So, in this case again the local weights are computed, the alpha or E is computed in the same fashion, alpha is computed in the same fashion, and then the context is computed in the same fashion. Everything remains the same. Only thing or the modification that we have is only look at this portion of your Ht and not everything else. Okay. So, by doing this we believe that the contextual information would be very clear, and there will not be not much of loss in terms of knowing what is the neighborhood for this word here. So, when I say neighborhood for this word here, it could be la, la and so on, right. So, it should be able to remember the local context very well than the global context, that is the idea. So, and then for the next word, if you want to get here, we will have 3 of this, 4 of this, depending on how much context that you want to feed in into your attention vectors. Okay. So, this is another model that you want to that you may want to know. So, at the very high level, if you look at this, we have included an attention layer, we have the encoder here, and then we have the decoder here. So, both of them combine the values from here and create the attention, whether it is global or local, and then that attention layer provides that input to the decoder, and then the output is computed. So, this is a very standard approach and a simple diagram that depicts both global as well as local attention in this in one. Okay. So, only here we see how only in this we will introduce the global and local models.